Dear all, welcome back. In this class, we will discuss one of the main drawbacks of value at risk, that is to say, the fact that VaR, as a measure of risk, is often not coherent. But what does that mean?
In general terms, a risk measure is a function that is used to quantify risk. It is meant to determine the amount of an asset, say money, to be kept in reserve. The aim of a reserve is to guarantee the presence of capital that can be used as a partial cover if the risk event manifests itself, generating a loss. Do you remember what we have said during week 1? From a mathematical point of view, a measure of risk is a function phi that maps from the linear space of losses to the extended real line. The space of losses is linear. This simply means that it allows operations such as addition and scalar multiplication. When we associate our measure phi to a loss, what we get is a number. Notice that we consider plus and minus infinity as numbers. A number that we can use to determine our reserves. A measure of risk is said coherent if it is monotone, subadditive, positive homogeneous, and translation invariant. The mathematical definitions are given on screen. Monotonicity means that if Z1 and Z2 are two losses and Z1 is smaller than Z2, then the value of the risk measure in Z2 is greater than the value of the risk measure in Z1. Subadditivity means that the risk measure assigned to a combination of losses, a portfolio, is smaller than the sum of the risk measures assigned to the single losses. Positive homogeneity says that, for a non-negative scalar A, phi of AZ is equal to A times phi of Z. Finally, for translation invariance, we can give two definitions: a mathematical one, in which adding a constant to a loss does not change its risk profile, and a second one, more economical, in which adding a scalar to a loss reduces risk by the same quantity. If one of these properties is not respected, a measure of risk is not coherent. Sometimes we can also assume the risk measure to be normalized, even if this is not strictly necessary for a risk measure to be coherent. But what are the economic interpretations of these properties? Monotonicity tells us that it is always possible to have an ordering of losses and of their risk profiles. Subadditivity guarantees that our coherent risk measure is in favor of diversification of risk. The risk of a portfolio of loans or securities, and therefore of their potential losses, should be smaller than the simple sum of single risks. Positive homogeneity simply tells us that risk is proportional. If your portfolio may lose $10 and you double the amount of money in that portfolio, you may expect a loss of at least $20. Finally, we have translation invariance. In that case, the idea is that if we add a non-risky quantity to our risky elements, risk cannot increase. From a strictly economic point of view, it can even decrease. Why? Imagine you add liquidity to a portfolio. In the short run, we can assume money to be risk-free. That is, we can ignore inflation. Now, the overall risk of our portfolio decreases, since it already contains some liquidity that can be used to hedge risk. Let's now consider an exercise to show that, unfortunately, the value at risk is not always coherent. In particular, we show that the VaR is not generally subadditive, hence it appears to be against diversification. We have two independent portfolios of bonds. They both have a probability of 0.02 of a loss of 10 million pounds and a probability of 0.98 of a loss of 1 million pounds over a 1-year time window. The 97.5% VaR is 1 million for each investment. What is the joint value at risk of a portfolio made of the two investments? Since we are assuming independence, computations are rather simple. Let's start by writing down the usual table of losses and their probabilities. In this case, it's easy to see that for each single investment, the 97.5% value at risk is 1 million. 97.5 is in fact smaller than 98%, the probability of 1 million loss. Now, let's build another table containing the portfolio that combines the two investments. The smallest loss we can expect is in the case in which the two independent investments make us lose 1 million each. The total is therefore 2 million pounds. The probability of this event is 0.98 times 0.98 equal to 0.9604. Then we have a possible joint loss of 11. This can be obtained as 1 million loss from the first investment and 10 from the second, or vice versa. Hence, the probability is 0.98 times 0.02 times 2. Finally, the worst scenario is the one in which we lose 20 million. Here, the probability is 0.0004. As usual, we can draw a graph of the empirical cumulative distribution function of losses. On the x-axis, we have losses, while on the y-axis, we have the cumulative probabilities. The 97.5% VaR of the portfolio is obtained by drawing the usual horizontal line passing through 0.975. The line intersects our ECDF at a point which corresponds to a loss of 11 million pounds. This is our value at risk. Now, notice the following. The joint VaR is 11 million pounds. This quantity is definitely larger than the sum of the two VaRs of the single investments, which is 1 plus 1 equal to 2 million pounds. This simple example shows that value at risk is not subadditive, hence it is not coherent. Okay, and what about the expected shortfall? In that case, we can easily show that the expected shortfall is always coherent, and in particular, it is always subadditive. It is a nice exercise to show that on your own. In general, we can say that the expected shortfall is always coherent, while the VaR is not. However, there are special cases in which the VaR is coherent, since it shows to be subadditive. For example, if the loss distribution is a Gaussian distribution, it is not difficult to show that the value at risk is coherent. This holds for all elliptical distributions. Can you think of a simple example showing this? Okay, let's now change topic and consider backtesting. Backtesting is a validation procedure often used in risk management. The idea is simply to verify the performances of the chosen risk measure on historical data. Consider a 99% credit VaR. What we want to check is how that value would have performed if used in the past. The idea is to count the number of days in the past in which the actual loss was larger than our 99% VaR. If these days, called exceptions, are less than 1%, 1 minus alpha, then our backtesting is successful. If exceptions are, say, 5%, then we are probably underestimating the actual value at risk. Naturally, it may also happen that we overestimate value at risk. Standard backtesting is based on Bernoulli trials generating binomial random variables. If our VaR alpha is accurate, the probability p of observing an exception is 1 minus alpha. Now, suppose we look at the total of n days and that we observe n smaller than n exceptions. What we want to compare is the ratio mn and the probability p. To perform this test, we use the binomial distribution. The binomial distribution tells us that the probability of observing more than n exceptions in n days is the one you see on screen. The idea is that once we have chosen a significance level for the test, say 5%, we'll look for the right tail probability of our binomial. If this probability is smaller than the chosen significance level, we reject the null hypothesis that our value at risk is okay, thus rejecting the VaR. If the probability is greater than the significance level, the value at risk appears to be okay. Notice that this is true if we test about the underestimation of value at risk. In the case of overestimation, we are interested in the left tail, but the philosophy is the same. An exercise will make things easier. We want to backtest our value at risk using 900 days of data. Alpha is 0.99 and we observe 12 exceptions. According to our value at risk, we expect only 9 exceptions, 1% of 900. Should we reject our VaR? What happens with 20 exceptions?
We will solve this exercise using R. So, let's go.
In R, it is very easy to compute the probability we are interested in, simply by using the p-binom function. Since we are interested in a right tail probability, given that we are interested in seeing whether our value at risk is underestimated, we can simply type 1 minus p-binom of 11, 900, 0.01 true. 900 is the number of days, 0.01 is the 1 minus alpha level, and true is an option we use to tell R that we are interested in the cumulative distribution function of a binomial. But why are we typing 11 and not 12? Simply because the binomial is a discrete distribution. Hence, the probability of observing 12 or more exceptions is equal to 1 minus the probability of observing 11 or less exceptions, which is what p-binom 11, 900, 0.01 true computes. I refer you to the help guide of R for more details about the use of the function. Let's say that we choose 5% as significance level for our test, but it could also be 2% or 1% or what you prefer. Since 0.1960 is greater than 0.05, we cannot reject the null hypothesis, and this means that our value at risk is correct. In case of 20 exceptions, on the contrary, we obtain 0.0009. This quantity is smaller than 0.05, hence we reject the null hypothesis. Our value at risk is underestimating risk. Notice that the results hold true also if we choose a 1% significance level. As for all tests, the choice of the significance level is very important. In the case of overestimation, we are no longer interested in the right tail, but in the left one. Hence, instead of 1 minus p-binom, we just consider p-binom, the cumulative distribution function. In other words, we are interested in the probability of observing 2 or less exceptions for in the second case. You will just need a little practice, but the methodology is simple. If you have problems, do not forget to use the course discussion forum.
Okay, goodbye.